So let's talk a little bit about acid structure and strength and being able to look at the chemical formula, which would tell us something about the chemical structure of the molecule and how that relates to acid strength. And so hopefully through this video, we'll be able to explain the trend between chemical structure and acid strength. And then also from that, be able to apply that by predicting relative acid strengths from chemical structure. So we think of some general guidelines that we're thinking about with regards to strengths of acids. The stronger the acid that's dissolved in water, the better it donates protons, or the more that it donates protons, which would correspond to a larger Ka value. Now reminding us when we're looking at a generic acid reaction where we would have the transfer of that proton from Ha to water, which is going to give us hydronium and the A- ion. The equilibrium constant for that, which would be our Ka value, is relative to how much of that Ha is transferred, the H+2 water, basically how many hydronium ions and A- ions we get. The more we get, the larger that Ka value. Now we think of how this corresponds back to structure. So I think this is something that we would observe experimentally. Right, we're going to look at the Ka value, but if we look at structure, we think the weaker the Ha bond, the easier it is for that bond to break. Basically, the easier it is for that substance to donate that proton, because we're going to just let that proton go. And then therefore, the stronger the acid, the more protons it would donate in water. So we have these two general ideas when we're looking at acid strength. The more polar the Ha bond, the weaker the bond, and the longer the Ha bond, the weaker the bond. Now we may see there's conflicting results between these, but we'll look at which of those two may be specifically more important when we're looking at two different types of acids and comparing them. So we're going to talk about two broad categories of acids: binary acids, meaning two elements. So that's going to be H with some element X and some number of hydrogens. So it could be one hydrogen, two hydrogen, three hydrogens. And we're going to see that we're going to compare maybe two types of groupings. So here we're going to compare first H2SE, and then we're going to compare H2S and HCl. So we have these two pairs of groupings, and we have H2SE. So we would see if we were to draw our H2SE, maybe it would look something like that. We would draw our H2S, would look something like this. Now, if we were to draw them structurally and kind of their geometry, they would both be bent molecules. But here we're just drawing out what's bonded to what. So if we compare these two things, and again, we bring them back to the general guidelines of the more polar the bond, the weaker the bond, the longer the bond, the weaker the bond. And again, thinking about the weaker the bond, the stronger the acid. And so let's compare these two things if we're comparing selenium and sulfur. So if we think of selenium is a less electronegative atom, sulfur is a more electronegative atom. And if we think about the trends in electronegativity, we would see that our electronegativity increases as we go across the periodic table and up the periodic table. So if we think of the general trend that we would observe. Now, because selenium is less electronegative, sulfur is more electronegative, this is going to make the hydrogen-sulfur bond more of a polar bond, and the hydrogen-selenium bond less of a polar bond. So we see that there's those two general ideas. Again, we're talking about polarity, but then we also want to think about what is the other factor as we think about size. And so now, again, we thought about this idea of polarity. So now let's think about size. Selenium is a larger atom. Sulfur is a smaller atom. Now, what does that mean for us with regards to the bonds that we'd see? That would mean the selenium, let's just draw it longer. Bond, hydrogen bond is longer, and the sulfur hydrogen bond is shorter. And if again we think about the general trends that we would observe, we think of atomic size or radii increases as we go from right to left and then down the periodic table when we're looking at our atomic radius. Okay, so again, in this case, if we look at the periodic table, we would notice that selenium is just below in the same group as sulfur, and so it's a bigger atom. So now we have these two observations that we've made. The hydrogen-sulfur bond is a shorter, more polar bond, whereas the hydrogen-selenium bond is a longer, less polar bond. And what we observe here is that in this case, selenium with hydrogen is a stronger acid than sulfur with hydrogen, even though the hydrogen-sulfur bond is more polar. And so one kind of major observation that we can make, if we compare binary acids in the same group, right? So the same column on the periodic table, what we notice is that we are going to compare the fact that the larger atom is going to have a longer hydrogen, whatever that atom is, bond, which is going to make it be a weaker bond, which is going to make that a stronger acid. So we can make this observation that we see when we're comparing things in the same group, our atomic size is what is going to predominate the factor that affects bond strength, which is also going to affect acid strength. Okay, so now we compared two things in the same group. Now let's maybe compare two things in the same period, so the same row. So now we have HCl and H2s. So again, let's go ahead and make our distinction between these. Okay, so we'd have HCl, and then we have H2s for our two structures that we would see. And so now if we compare these, we would see that chlorine, we again go by this guideline right here. Chlorine is further to the right of sulfur, so chlorine is a more electronegative atom, whereas sulfur is a less electronegative atom. What does that mean for our bond? That means the hydrogen-chlorine bond is more polar, and the hydrogen-sulfur bond is less polar. Okay, so now we can go ahead and make those observations there about the polarity. Now let's go back and let's look at size. Again, we see, if we look again at our trend here, what we would notice is that chlorine again is further to the right, so it is smaller. So chlorine is a smaller atom. Sulfur is a larger atom. And what does that mean for us? That means the hydrogen-chlorine bond is shorter, whereas the hydrogen-sulfur bond is longer. So again, now we have these two observations about the size and polarity of our bonds. And now let's go ahead and make some general observations. We know that our hydrogen-chlorine bond is weaker because our hydrochloric acid is a stronger acid than our hydrosulfuric acid, or H2S. And so now we're here, in this case, we are comparing acids of atoms in the same period. So again, that is the same row of the periodic table. What we'll notice here is that what's most important when we're looking at the strength of this acid is the fact that we are looking at the polarity of the bond is going to lead to a stronger acid. Now, and again, when we're looking at this, what we're thinking about is the more electronegative atom is going to lead to a stronger acid. So the more polar bond is going to lead to a weaker hydrogen, whatever it's bonded to, bond, which is going to make it a stronger acid here. So again, we think about the variables that affect this. Importantly, we're thinking about polarity when we're looking at the atoms in the same period, whereas we'll see that the size is what predominates the strengths of an acid comparing them in the same group, so the same column versus the same row. Now again, we see that these two factors are varying, and the reason for that is that the magnitude of difference, right? This is a greater magnitude, right? The difference in the electronegativity than we would see for our bond length. So our bond length is slightly smaller for hydrogen chlorine than it is for hydrogen sulfur. But the polarity is way greater because chlorine is much more polar than, much more electronegative than sulfur. Whereas if we look at our selenium and sulfur, what we'd see is that the bond difference, this magnitude, is so much greater for the bond length for hydrogen and selenium versus hydrogen and sulfur compared to the difference in polarity. We would observe that because of that, that's going to be the factor that predominates the strength of this binary acid. So again, we're comparing these. We need to think about which one, are we comparing them in the same group? Are we comparing them in the same period? And how does that relate to the strength of the acid? So this is dealing with binary acids. So let's go ahead and look at our second group, which would be oxyacids or oxoacids, depending on who you ask, tomato, tomato. And so now what we're looking at here is we're looking at an acid with some number of hydrogens, some element, and then some number of oxygens. That's why we call it an oxoacid. So again, we're going to look here thinking about the two factors. The longer the bond, the weaker the bond, the stronger the acid. Okay. In addition to that, the more polar the bond, again, the weaker the bond, the stronger the acid. So again, those are two guiding factors. So we need to look at what's going to differ between these. Now, as we look at our oxoacids, one important observation to make is that our hydrogen is always bonded to an oxygen here. So it's always, in all of these, our hydrogen is bonded to oxygen in all oxyacids. Now, what does that mean? That means the hydrogen-oxygen bond length is basically the same. So what we notice here is that our bond length with oxyacids, well, let's just strike that out. That's not actually going to affect any of our strengths of acids. And that is because all of them are bonded, all of our hydrogens, no matter the oxyacid, is bonded to an oxygen. So therefore, the size of atom that it's bonded to is the same. And so we're not going to see any difference in a longer or shorter bond. So what we'll see here is the factor that we're going to focus on now is, well, what's going to affect the polarity of a bond? We'll see there's kind of two general factors that we can look at. Here, what we're comparing is the number of oxygen atoms, and when we're thinking about this, with the same element in our oxyacid. So again, we're comparing chlorine and chlorine with 2 versus 3 oxygen atoms. And what we'll notice here is the one that has more oxygen atoms is a stronger acid. And we think, why would more oxygen atoms lead to a stronger acid? So we go back to this idea of the polarity of the bond. Well, what we know about oxygen, oxygen is a very electronegative atom. So if we continue to add more of these very electronegative atoms, what that's going to do is that's going to generate this whole kind of group that we're thinking about of 2 oxygen atoms in a chlorine versus 3 oxygen atoms in a chlorine. That's going to lead to a more polar bond when we have more and more and more oxygen atoms. While more polar bond is a weaker hydrogen, whatever it's bonded to, in this case, the ClO3 minus or the ClO2 minus, a weaker HA bond, which is going to lead to a stronger acid. So again, comparing when we have the same elements, so chlorine, and then we have 2 oxygen atoms versus 1, 2, 3 oxygen atoms. And so the more oxygen atoms we have, the more electronegative that whole group that we can think to that our oxygen is bonded to. Now let's go ahead and move over here to our second type of comparison that we can have. Again, we have the same number of oxygen atoms. So here what we're doing is we're comparing something with the same number of oxygen atoms. So we can think there that is not going to affect the electronegativity of this whole group. Now what we notice, the only difference here is the element bonded to our oxygen atoms in our oxy acid. And so we notice here we're comparing chlorine versus iodine, and again we're comparing the whole electronegativity of this whole group, right? We want to compare the electronegativity of that whole group. Is that whole group very electronegative? Is that whole group not as electronegative? Because the more electronegative the group of, what we would classify as A in HA, right? The more electronegative that group, the more polar the bond. We think the difference here is iodine and chlorine. And so what we notice is that the more electronegative our element X in our oxy acid, that's going to lead to a more electronegative group. And so we see here the more electronegative element X, that's going to lead to a weaker bond. Again, more of a polar bond. And because that leads to a weaker bond, that's going to lead to a stronger acid. So now we see, hopefully we had a chance to investigate the strengths of these, the relative strengths of these two types of acids, oxyacids and binary acids. And we see there's something that's very different about them. Specifically, our oxyacids are always bonded between hydrogen and oxygen. So we notice that bond length doesn't change. It's just simply electronegativity that's going to affect our strength of our acid. So now you'll notice on the handout that I gave you, we have some more practice problems. So what I would advise you to do, pause the video and answer these questions. Once you've had a chance to answer them, think about them on your own. I'm going to talk through them and then come back and watch the video to read through and talk and see what kind of we thought with regards to these acid strengths. So now that you had a chance to pause the video and predict which is going to be a stronger acid, let's look at this when we're looking at these two different groupings. So again, we have H2S, H2SE. When we look at this, we see that this is a binary acid, which means we need to think about, is the size of the acid going to be important, or the electronegativity of the atom that our hydrogen is bonded to important, right? And the way that we identify which of those we need to think about, we need to look at these two, and we see these are in the same group, sulfur versus selenium. So when we're comparing things in the same group, what we'd see here is that size is going to be the most important factor when we're looking at strength of acids. And what we notice is that we have selenium and sulfur, and we would see selenium is a larger atom than sulfur, just looking at our periodic trends. And then we see that because it's a larger atom, that means the selenium hydrogen bond is longer, which means the selenium hydrogen bond is weaker, and that means that this would be overall a stronger acid. So again, this is a binary acid. We looked at the size of the atoms because they are in the same group. The difference in size is much greater than the difference in electronegativity. And what we observe is that our H2SE is our stronger acid. Now here we have our second grouping, H2SO3 versus H2SeO3. And again, we still have selenium and sulfur, but here we're dealing with an oxy acid. And we notice that the two factors that affect the oxy acid is the electronegativity of our element that we have inside of our oxy acid and the number of oxygen atoms. Well, in this case, we notice that we have the same number of oxygen atoms. We can go ahead and square that off and note Okay, that's not going to affect the relative strengths of these two. So then what we need to do is we need to compare the electronegativity of selenium versus the electronegativity of sulfur. And what we would notice is that the electronegativity of sulfur is greater than the electronegativity of selenium, which would mean that this whole group, the SO3 versus the SeO3, is going to be a more electronegative group. Well, because it's a more electronegative group, so we think of the SO3 versus the SeO3 2 minus group, this is going to be a more electronegative group. This is going to be a less electronegative group. And because of that, that's going to lead to the hydrogen to that whole group, we're just going to call A, right, which would be our whole group. That's our SO3 2 minus. That hydrogen to whatever that group is bond will be more polar because that whole group is more electronegative, and that's going to lead to a weaker hydrogen to that whole group bond, which is going to make that H2SO3 a stronger acid than our H2SeO3. And again, we're comparing these relative acids to each other. Now what we're going to do is we're going to apply this a little bit in thinking about two different types of equilibria. Okay, so here we have our H2S and H2Se and their conjugate bases. So again, we have H2S would be an acid. Its conjugate base, we take away an H plus, is HS minus. Likewise, our H2Se is an acid. Its conjugate base is HSE minus, okay, because we take away that H plus. Now we look at these and we think, okay, we know the relative strengths of these. We know that our H2Se is the stronger acid. So let's go ahead and label that under here. That is our stronger acid. And this is our weaker acid. And what we're trying to do is identify, are we going to have more reactants at equilibrium, or are we going to have more products at equilibrium? And we look at this and we think something that is a stronger acid, we notice here this is really good at donating protons. Well, if this substance is really good at donating protons, what you'll notice is it will not hold on to them. And so that would mean that the concentration of H2Se will be relatively small in this because it wants to give its protons away. It's good at giving its protons away. It really wants to give its protons to HS minus. And so because of that, we're not going to see much of the H2Se at equilibrium. And so we'll notice with our weaker acid, we will see more of the H2S than our stronger acid, H2Se, at equilibrium. Well, we think, how does that relate back to favoring the reactants or favoring the products? That means we're going to have more reactants at equilibrium and fewer products at equilibrium. Okay, so here this reaction favors our reactants. Again, that's because we're going to have more of our reactants, more of our weaker acid at equilibrium. We'll connect that back to our Kc value being less than 1, greater than 1, or equal to 1. If we have something that favors our reactants, meaning they have a higher concentration at equilibrium, we would say, okay, well, that means if our Kc value is products over reactants, that would mean we're going to have a Kc less than 1, or a small Kc. It's also another way we could say it, small Kc value, because we have a lot of reactants at equilibrium, a very small amount of products at equilibrium. Now let's go ahead and apply this to our other grouping of acids that we have, H2SO3 versus H2SeO3. And again, let's go ahead and label our acids and conjugate bases. So here we have H2SO3 would be an acid. Its conjugate base would be HSO3 minus, right? We take away an H plus. Then we have H2SeO3 is our acid, and we go ahead and take away NH plus, and we get HSEO3 minus. That would be our conjugate base here. And now again, let's go ahead and label our stronger acid and our weaker acid. So we already said that our H2SO3 is our stronger acid, and our H2SEO3 is our weaker acid. So let's label that. This would be our weaker acid. This would be our stronger acid. And again, we think about the same idea we just thought about. Our stronger acid here is much better at donating its protons, meaning we're going to see a very small concentration of H2SO3 at equilibrium because it is good at donating a proton. That's what it means by it being a stronger acid. H2SEO3 is worse at donating a proton. Again, we're comparing that to the acid that it's partnered with, the H2SO3. And because it's worse at donating the proton, we will see a larger concentration of H2SO3 at equilibrium. And again, we're comparing that larger than our H2SO3. And so that would mean we're going to have more products here at equilibrium. And with more products, that would tell us that this reaction favors the products or favors the right, however we want to look at it. And when we say favors, that means they have higher concentrations at equilibrium. And because we're going to have more products at equilibrium, we're going to have higher concentrations of our products. That tells us that we're going to have a Kc value that is greater than 1. And again, reminding us our Kc expression is the concentration of our products divided by the concentration of our reactants at equilibrium. And so because we have more products at equilibrium, that means we're going to have a Kc value greater than 1. Now, hopefully you had a chance to think through those ones on your own first and check and see what you got. And we're going to see here, this gives us the ability to apply the structure of a molecule onto the idea of how strong or weak that acid is when we're comparing 1, 2, or maybe 3 different acids to each other.